Okay, so I would like to talk today about magnetic resonance imaging with nanomechanics. Most of what I'm going to talk about is research that was pursued at IBM while I was a postdoc, but hopefully at the end of the talk I will start to tell you how we want to use some of the techniques that we picked up there in our new lab in Basel. Okay, so as I said, the topic will be nanoscale magnetic resonance imaging, and it's going to involve a few different subtopics. We're going to talk a little bit about micro and nanomechanics, also about the physics of small spin ensembles, and a little bit about nanoelectronics and nanomagnetics. All of these three parts are sort of critical parts, critical pieces of physics that go into the task of nanoscale magnetic resonance imaging. So most of you are probably familiar with magnetic resonance imaging. Maybe some of you have even had one of these done in the hospital. This is in fact an MRI of a colleague of mine, Christian Dagan, who is actually a graduate of the ETH. And this is a picture of his brain. And what's really nice about these techniques is that you can look inside Christian's brain, but you don't have to cut Christian open to look inside. So Christian is alive and well and starting his own lab at MIT, but we have this nice picture of the inside of his head. So it's a true three-dimensional imaging technique. It's chemically selective. So here we're looking at the proton density inside his brain, but in principle we could look at the fluorine density or other kinds of isotopes that are NMR active. Again, it's non-destructive. We don't have to irradiate him with gamma rays or something like this. The main drawback, I would say, is that you require many, many nuclei to create one, let's say, three-dimensional pixels. It's something like on the order of at least 10 to the 12 nuclei are involved in a signal coming from one pixel. So what we would like is we would like to do this at the level of a single nuclear spin. So the goal that was put forward some years ago now was to try to do the same kind of three-dimensional chemically selective imaging, but on the atomic scale. So for instance, if someone gave me a macromolecule like this, whose structure we didn't know, I could use this technique to place in space the position of each NMR active isotope. So to sort of put this kind of an imaging technique or this hope for an imaging technique in context, we should just think about sort of common objects and their size scales and their sort of relative numbers of spins, of proton spins that comprise them. So we have a very nice imaging technique that I just mentioned, MRI, which sort of lives in this region here, and when you push it very hard, can get you down somewhere to the 3 or 4 micron resolution range. We have other techniques like nuclear magnetic resonance, which allow us to learn something about single molecules or distance between bonds and angles, but it's not really an imaging technique per se. And then we have all kinds of other advanced imaging techniques that live in these areas. And they're all very nice, but most of these essentially give you information about surfaces and don't have the three-dimensional capability of MRI. So what we would like to do is use something called magnetic resonance force microscopy to bridge this gap where between MRI and NMR. We would like to try to push the resolution to get to this single atomic resolution. Okay, so this was an idea that was put forward in the 90s by John Seidels and Dan Rugar at IBM. And it's essentially, it's quite a simple idea. So if you think of a normal, conventional, inductively detected MRI experiment, you have some magnetic moment, and it's near or nearby or inside an inductive coil. And when the magnetic moment flips, it will change the fields inside that inductive coil. Now there will be a signal induced onto the coil, and you can measure that current impulse or voltage impulse on the coil. Now the amount of signal to noise is essentially proportional to how much you fill up this coil with magnetic moment. The more the magnetic moment fills the coil volume, the bigger your signal to noise will be. And that's basically because when the magnetic moment flips, it's changing the field inside the coil, relatively speaking, much more when there's more magnetic moment than when there's less. So that turns out to be a very nice way to pick up signals from large samples where the magnetic moment of the sample fills up a lot of space in the coil, but it's not so good for very small samples. It turns out to be very hard to make very, very small inductive coils. So when you're talking about nanometer scale samples, you get very bad signal-to-noise using this technique. So a technique that was put forward was based on a different principle, but equally simple. Let's say we have some compliant cantilever, something that bends when you apply a force to it. And you put a magnet on the end of that cantilever. When a nearby magnetic moment flips, there will be a force on that magnet, and it will bend the cantilever. If you can measure that bending, you've measured the presence of this magnetic moment. And with recent MEMS and NEMS technology and micromagnetic technology, you can make this kind of detection technique much, much more sensitive for small samples. So this is the kind of technique that I will be discussing today. So this is not really a new idea, mechanical detection of magnetic resonance. In fact, it was first done in the 50s and 60s. This is an example of paramagnetic resonance experiments done in the 60s in Pisa, based on a similar principle. Essentially, the resonance sample was absorbing some microwave field, it was absorbing some angular momentum, and then you were measuring the absorption of that angular momentum by measuring the bending of the sample at the end of a very long string. And this was actually quite a nice measurement for the time, but was not so sensitive compared to sort of normal inductive techniques. Now that we have the ability to make MEMS and NEMS, so very sensitive mechanical elements, such mechanical techniques are really becoming the best way to measure magnetic resonance signals from small spin ensembles. So the first kind of modern mechanical detection of magnetic resonance was done in the 90s, again at IBM by the Rugar group, where they measured some sample on the end of a standard AFM cantilever, and they were able to demonstrate the detection of magnetic resonance. And this early work, in about 10 years, led to the detection of a single electron spin resonance using a mechanical scheme. So this was all, what I've talked about until now was all involving electron spins. Of course, what would really be nice is to detect nuclear spins, but that turns out to be about 1,000 times harder because the moment of the nuclear spin is about 1,000 times smaller than the electron magnetic moment. But nevertheless, people have been working on that as well. In fact, here at the ETH, the group of Beat Meyer has been working hard on NMR detected mechanically, and they've developed a lot of very nice techniques to apply spectroscopy and imaging techniques that we learn from classical NMR to these mechanically detected techniques. Okay, so if we're going to push this kind of mechanically detected technique to detecting very, very small numbers of spins, what do we require? Well, we're going to require an extremely sensitive force sensor, a very strong magnet. You can imagine the force between this magnetic moment and this magnet will go something like the gradient of the magnetic field. And then we'll need some way to controllably flip these magnetic moments so that we can detect the presence of the moments. So I'm going to go through and sort of show you how we do all of these things and then put this together into some kind of an imaging technique. So let's talk first about very sensitive force sensors, which are coming about from micro and nanomechanical technology. So mechanical force transducer is what we require. This is a very simple example of a mechanical force transducer. It's just a cantilever. When you push down on it with a force F, it will deflect by a displacement X. You can roughly treat this like a Hooke's law spring. And naively speaking, if you want to measure small forces, you basically want a very, very small value for the spring constant K. That will give you a large displacement for small forces. So we can apply sort of classical ideas like Euler-Bernoulli theory to this kind of a cantilever, and we will come up with some expression for the spring constant. And we will find that it goes something like the width times the thickness cubed over the length cubed. So what does this tell you? It tells you essentially that you should try to make a very long and thin cantilever to make a very small spring constant. Of course, if you think about the problem in a little bit more depth, you'll realize that when you want to measure very, very small forces, there's going to be another limit here, which is really thermodynamics. At some point, for small enough forces, the thermal force, or the Brownian motion of this cantilever, will start to limit you. So if you want to measure a force, that force better be bigger than the force that you get from just thermal excitations of the end of your cantilever. And you can try to figure out how does that go. So let's see. Well, then you have to start thinking about the fluctuation dissipation theorem and the spectral density of essentially thermal excitations in the cantilever. And the spectral density looks something like this. It has some Boltzmann constant times the temperature, and then some term gamma, which is, let's say, the dissipation of the cantilever, or the energy loss of the cantilever. You can rewrite this also in terms of the resonant frequency of the lever and the mechanical Q factor and the spring constant. And essentially this tells you something about the spectral density of these random thermal forces. So you can also think about this as a minimum detectable force. Any force that you want to measure should be larger than this thermal force. So we can write this thermal force out like this, with the spectral density times some bandwidth, which is usually given by your measurement conditions. And we can have an expression like this. For the best kind of mechanical sensor, we should minimize this expression. So we should try to make a cantilever that minimizes this. So how can we do that? Well, again, let's write out that thermal spectral density, and let's look at some sort of different kinds of cantilevers. Typically, you want to work at some fixed temperature, so let's say that we keep our temperature constant, and also you would obviously like to have a very high quality factor of your cantilever, but as yet we still haven't really learned how to make this, how to really control this. And sometimes you can make the Q very high, sometimes you can't. I would say that this is still a little bit mysterious. So what I'm going to do is take these terms out, and let's say that they are given. We're given a certain temperature, we're given a certain Q for our oscillator. So what should we do to the oscillator to make sure that we get the lowest possible thermal force noise? Well, we should minimize this term here, the spring constant divided by the resonant frequency. And if we, again, apply very simple Euler-Bernoulli equations, we can write this in terms of some geometric parameters, so some mechanical parameters and width, thickness, and length. And we quickly find that this term goes like the width times the thickness squared over the length, and so therefore so does the thermal spectral density. So again, we've come to the conclusion that if we want a really sensitive force detector, it should be very long and thin. So if we are looking at these various different cantilevers, it actually turns out that this one is probably the best one to use. And in fact, I'm going to, when I continue my talk, you'll find that this is the kind of lever that we typically use. This is about 100 microns long and 100 nanometers thick. And in fact, the best force resolution achieved by any sensor was basically done in 2004 by this kind of a single crystal silicon lever of the kind I just described. They achieved a minimum force resolution of about 1 attonewton per root hertz. And recently, Conrad Lader and some coworkers at Gila in Colorado achieved a similar force resolution, or maybe even lower than this, using something like a very, very long vibrating string made of aluminum. So you can see, again, the sort of geometry that we came up with using our very simple Euler-Bernoulli treatment is correct. You want something that's very long and thin if you want a sensitive force sensor. So let's say we really wanted to go to the best possible force resolution. If you're thinking about something long and thin, well, maybe you should use something like a nanotube or a nanowire. And in fact, there's been recent work at Delft in the Netherlands where they've been looking at some mechanical resonances of single nanowires, so-called ultra-clean nanotubes, ultra-clean nanotubes. And they basically measure very, very high Qs for these nanotubes, very small masses, and fairly high resonant frequencies. And they can cool these down to very low temperatures. If you take this resonator and you calculate what is the minimum measurable force from this force sensor, you'll find something that's about 100 times better than anything we've ever seen. So it would be great if we could be able to use this device as our force sensor. But the trick is that these kinds of devices are really only force transducers. They transform force into mechanical displacement. Then you have to find some way to measure that mechanical displacement. For the cantilevers I showed you, that turns out to be quite simple. You can just shine some light on them, and they're rather big in the lateral direction, and they will either deflect that light, or you can put them in an interferometer and you can measure the fringes from their vibration. For something like a nanotube, measuring the thermal motion of this thing is actually non-trivial and has not yet really been done. So the current state of the art, I would say, is something like this. But maybe in the future, you might see force sensors that look more like this. So, okay, we've come up with some kind of very nice force sensor which we're going to use. Let's say something like that. Let's talk about nanomagnetics and small magnets that produce very large gradients. So some of the first magnets that were used were actually very simple. Someone would take a very strong magnet like samarium cobalt, smash it with a hammer, find some small piece of this magnet, and glue it to the end of a cantilever. Okay, it sounds very crude, but in fact that turns out to be quite a good way to get a strong gradient. And that's in fact what's being shown here. These are pictures from the IBM group from their experiments in 2004. They would essentially take a very small samarium cobalt particle, glue it on the end of a very thin silicon cantilever, and then take a focused ion beam and mill it to whatever shape they wanted. So make it very pointy so that the gradients would be very strong. And with this method, they achieved gradients on the order of 1 or 2 times 10 to the 5 Tesla per meter. Of course, the gradient falls away with distance, so I can give you this kind of a value at about 25 nanometers away from the magnet. So this is a nice way to do it. Of course, it's very tedious, and you can wonder about what happens to the magnet when you shoot focused ions at it. It probably doesn't like that very much, and the magnetization probably suffers. So a better way would be if we could pattern a magnet on the end of the cantilever. And some groups have tried to do that, to actually use lithography to put nanomagnets on the end of cantilevers. That turns out to be quite difficult. It's much easier to put magnets on surfaces, and this is an example of something like that. These are actually commercial structures that you can buy. These are very pointy triangles of silicon, and what you can do is evaporate some magnetic material on top of that, and then you come up with a very, very pointy magnetic film, which produces a very, very strong magnetic field gradient. This was also something made at IBM. It was basically a silicon pyramid with some layers of magnetic material evaporated on top, and actually this produced a much larger gradient at the same distance than the samarium cobalt magnets. And that was mostly due to the fact that they were using a different material, iron cobalt, which has a stronger magnetization. The problem with iron cobalt is that it's a soft magnetic material, so in order for it to be completely polarized, you have to apply a strong field, but that's not always such a bad thing. Okay, so this was one way to produce higher gradients. Finally, the best way that was found was to take this kind of iron cobalt material and evaporate it through a kind of a stencil, as you see here. What you see here are some iron cobalt tips in the middle of a fabrication process, where you have some kind of a mask here with some etched out caverns underneath it, and then you evaporate some iron cobalt through these holes, and you can make these very kind of almost cylindrical tips. And these provide very, very strong gradients of about 4 times 10 to the 6 Tesla at about 25 nanometers of distance. So this is a big improvement over the original more or less 10 to the 5 Tesla per meter gradients. But if you make some magnetic calculations and you assume sort of the ideal magnetization inside here, it's still the calculations say that you should have about 10 times higher gradients than you actually measure. So there is still quite some work to be done here in understanding how to make very small magnets that are producing very, very strong gradients. But this is essentially the state of the art at the moment. Okay, so we have very sensitive force sensors, very strong magnets. Now we need to understand a little bit about the physics of small spin ensembles. We're going to be measuring very few numbers of nuclear spins, so we should understand how they behave differently from large ensembles of spins. In a normal MRI experiment, you exploit the Boltzmann polarization of nuclear spins. So what you will realize, though, is that even at low temperatures like 4 Kelvin and high magnetic fields of about 3 Tesla, if you plot the spin polarization, this is not a normal way to plot polarization, but this is, let's say, spin up minus spin down, so the net number of polarized spins. If you plot spin polarization as a function of the number of spins in your sample, you'll see that it really quickly drops away. Okay? Now, it doesn't look so bad here until you put some kind of scales on the plot. So we can scale sort of number of spins with a volume. Okay, and you can see that very quickly as you get into the nanometer regime, the spin polarization rapidly approaches 1. And it's going to be very hard to measure a spin polarization of 1 in a kind of sample size of something like 10 to the 4. And in fact, this is essentially what's blocking most of the both conventional and early force-detected NMR experiments, just the lack of enough polarization. So what you find is that if you want to get to this kind of nanometer regime, you have to use a different kind of polarization. And so what we will use is essentially the statistical polarization. So you might ask me, what is the statistical polarization? Well, if I take 100 coins and I throw them in the air, the mean will always be about 50, but then there will be some variance around that mean that goes like root n, okay? So, and that variance around the mean is what we measure. So it has no definite sign, but there is a definite, it has a definite magnitude that we can measure and use for imaging. Okay, and so in the experiments that I will talk about today, essentially we were very much in the regime where the statistical polarization was much, much larger than the mean Boltzmann polarization. So if you think of the polarization as some kind of Gaussian, the mean of the Gaussian is very close to 0, but the width of it is much larger than the mean, and we actually measure the width of that Gaussian. Okay, so actually statistical spin polarization has been understood for a long time, and if you look at sort of the seminal paper on NMR by Felix Bloch in the 40s, you'll find a passage in there where he essentially discusses exactly this. He says that even in the absence of any orientation by an external field, you can expect a sample with n nuclei of magnetic moment mu to find a resultant moment of the order n to the 1/2 mu. Okay, so this is essentially the statistical polarization. He goes on later to say that, okay, we don't have to care about this polarization because it's extremely small. But now we're in the regime where samples are so small that we do have to care. And in fact, it will become our main signal. So this is, again, just writing down the Boltzmann polarization. If you write down what the statistical polarization is, just using the properties of a binomial distribution, you will find that in the typical limit here, where the magnetic energy is much less than the thermal energy, this is given by root n. Okay, so using the statistical polarization is nice, as I've been discussing, because we can measure small spin ensembles, because the statistical polarization for small spin ensembles is much bigger than the mean. But it's also nice because it eliminates the need to wait a time t1 for the sample to polarize. So in normal NMR experiments based on Boltzmann polarization, you essentially have to wait for the sample to polarize, which takes some typically long time t1 before you can do your experiment. In our case, you don't have to wait t1 because we're just looking for these sort of random statistical polarizations. Okay, so now we've talked about the magnet, we've talked about the cantilever, we've talked about the physics of the spins. Now we have to find some way to essentially control these spins, make them controllably flip up and down so that we can create some signal that we can measure. So what we're in the end going to want to measure is the force between some small magnetic tip and some, let's say, nuclear spin. Here I've drawn it as a single proton. In general, it could be many, many protons. So that force will go something like the gradient of the magnetic field times the magnetic moment. Okay, you might guess this is going to be a very, very small force. And in fact, it is extremely small. So let's say we take our best magnetic field gradient, 10 to the 6 Tesla per meter. What kind of force will we get from a single proton? Well, it's going to be 10 to the minus 20 newtons. Okay, it's a very small force, and doesn't look good for the problem, because if you just calculate van der Waals forces between the tip and sample at that distance, they're very, very much larger. If you calculate electrostatic forces at these kinds of distance scales, they're also much, much larger. Basically, the only force that's smaller is the weight of the proton in the gravity field. So you can imagine it's going to be a difficult measurement. And sort of to get this very, very small signal out of the noise, you use the magic of magnetic resonance. You use the idea that if you apply, in this case, a resonant magnetic field perpendicular so let's say we pass a current through this red block, which is supposed to be a wire. There will be some perpendicularly oscillating magnetic fields around this wire, and if we do that at the correct frequency, we will be on resonance with this nuclear spin. And then we can use pulse sequences from NMR to essentially flip the spin around almost any way that we like. So what will happen? That resonance condition between the magnetic fields around this wire and this proton spin will only be met in a certain position in space. Why is that? Because this magnetic tip is producing a magnetic field, but that magnetic field is highly inhomogeneous in space. Okay, it's changing a lot as I move away from this tip. So there's only a very small slice in space, this sort of hemispherical thing that I've drawn in this cartoon, where the spins are resonant with the RF radiation inside this wire. And only in this region in space will you be able to flip the spins up and down using the pulse sequences. So when your spin is outside that region and you have your pulses going through here, nothing will happen. When your spin is inside that region, it will start to flip around according to your pulse sequence. So which kind of pulse sequence will we choose? Okay, well, we choose a very simple NMR pulse sequence, which is an adiabatic rapid passage. So essentially what we do is we take the resonance, we slowly tune through the resonance frequency of the proton spin. And we do this many, many, many times. And every time we go through the resonance frequency, if we do this slowly enough, if we do it adiabatically, we will cause the spin to invert. Okay, so you can see here, we do it once, the spin component of the proton inverts. We do it again, it inverts another time. Okay, if we do this at the right frequency, we can essentially make these spins process at the resonance frequency of the mechanical oscillator. Okay, why would we want to do that? Well, if this spin is flipping up and down at the resonance frequency of the mechanical oscillator, there will be a force between it and the magnetic tip that's going to be changing at the frequency of the mechanical oscillator, and that eventually will drive this mechanical oscillator to oscillate very strongly, like someone pushing a swing at the right frequency. Okay, so in this way, we will basically bring this very small force out of the so-called noise and make it do something to the cantilever, which will be obviously measurable. Okay, so let's see if I can try to put this together in some kind of a movie. Imagine you have some spin, and we start doing these adiabatic sweeps. Now, when we start sweeping through resonance, what will happen? The position of that resonance condition will change in space as I change the resonant frequency, and every time that the resonance slice goes through the position of the spin will go through an adiabatic inversion. And we'll keep flipping and flipping and flipping. And if that spin flips at the correct frequency, at the resonance frequency of this mechanical lever, it will start to drive the motion of the lever. And then we measure that motion using the optical interferometer up here. Now, of course, this is just a cartoon. All of the size scales here have been exaggerated, but essentially this is the measurement method that we use. We essentially drive spin oscillations, the spin oscillations drive mechanical oscillations, and we measure that motion as our signal. Okay, that's in a perfect world where the spins are completely following our adiabatic sweeps. Of course, the world is not perfect. Everything has some correlation time, and so after some number of these sweeps, the spins will undergo some random flip. And that correlation time we call tau m. And if we take these kinds of dynamics into account, we could make a very simple simulation of, let's say, 1,000 spins to see what an ensemble of 1,000 spins would look like. What kind of signal would it give us? And that's exactly what this is. This is now the force on the cantilever as a function of time for 1,000 spins. And this is a simulation. And you can see from this signal that the noise looks pretty random. Of course, we're starting out with some random statistical polarization, so that would be expected. And you can see that it has some correlation time that you can sort of see here. What's important here is that the amplitude of this noise is given by the square root of n, the square root of the number of spins. So if you measure this on resonance, you know how many spins you're looking at, and you know their correlation time. So that's a simulated signal. This is essentially what the amplitude of your cantilever would do when it was driven by such a force. And if we take a real signal measured with this mechanical technique in calcium fluoride with about 10 to the 6 spins, you see something very similar. So now again, we're plotting the amplitude of oscillation of the cantilever as a function of time. This time it's measured. You can see there's some correlation time, and you can see it has some amplitude, which is going to correspond to the square root of the number of spins in the sample. This is what you see when you're on resonance and you're flipping the spins. When you go slightly off resonance and you're not flipping any spins, you see something like this. You can see that the noise is still noise, but it has a completely different character. The correlation time is much shorter, and the amplitude is much smaller. That's because this is just Brownian thermal motion from the cantilever, and this is actually spin noise. So you can look at this also in frequency space. That was plotted as a function of time, but you can take the same signals and look at them as a spectral density as a function of frequency, and you'll see that cantilever thermal noise is kind of a very broad, well, on this scale, very broad peak like this, which corresponds to the very fast correlation time. And then this spin signal is a very sharp peak sitting on top of that. And if you look at the signal in this way, you can tell the correlation time from the line width of this peak and the number of spins in the sample just by integrating under that peak. And essentially, when we do the measurement, that's what we do. We take such a signal, and we feed it to a lock-in amplifier, and the lock-in amplifier filters kind of around this bandwidth and integrates the signal through here and tells us about how many spins we're measuring. Okay, so now we've sort of gone through all the various pieces of the state-of-the-art mechanical magnetic resonance setup. Now I would like to put it all together to try to do something useful and make an image. So this is an experiment that was done at IBM while I was a postdoc there. And we used these kinds of cantilevers that I was telling you about, single crystal cantilevers, 100 nanometers thick and about 100 microns long. You can see these are extremely soft cantilevers. They're something like 60 micronewtons per meter. If you take a standard AFM cantilever, it's something like 1 newton per meter. And these kinds of cantilevers at 4 Kelvin give you a thermal force noise of about 4 attonewtons per root hertz. The other component, again, is this kind of RF source with a small magnetic tip on top. This is essentially a copper wire, which is about 2.5 microns long, about 1 micron wide, and 200 nanometers tall. We pass some current through here at a radio frequency of about 100 megahertz and produce oscillating fields around here. At the same time, we deposit a very strong gradient source here, an iron cobalt tip, which is about 250 nanometers tall. And the combination of this means that if you put your cantilever, you hang your cantilever right up here, about 100 nanometers away from the top of this tip, you will be in a region with an extremely large field gradient, something like 10 to the 6 Tesla per meter, and an extremely large rotating RF field of about 4 millitesla. And at the same time, because all of this is very compact, there's not a lot of dissipated power. So if you're working in a dilution refrigerator or some very cold refrigerator, you're not heating the system up too much because you're only dissipating a few hundred microwatts. And all of this is put at the bottom of a fridge, as I said, in some kind of a system that looks like this. Probably this just looks like a bunch of messy wires. But in fact, this is all designed to be vibrationally isolated from the pumps and from the system. You can see some very soft springs coming down here. There's some positioning equipment here, and then down here is where the cantilever and the microwire sit. So if you look at this in this geometry, you can see there is a lens here. The interferometer to measure the cantilever is in this direction. Uh-oh. That's not good. I think the power was not on. I hope it's on now. It looks like it is. Yeah, looks like it's okay. So maybe the plug wasn't in. Okay, I apologize for that. Have to plug in your computer. Okay. So as I was saying, the cantilever is pointing up, the interferometer is in here, and this microwire and magnetic tip are on this little sample holder here. So in fact, the real geometry is inverted from the cartoon that I showed you. The cantilever is hanging up, the magnetic tip is pointing down. But of course, on these scales, gravity doesn't matter, so you could orient it in any way you want. Okay, so this is the setup, and we just decided to try this with, try making an image of a very small sample to see what kind of resolution we could get. So we would like to do some kind of biological sample. So the sample that we chose was a tobacco mosaic virus. It's a nice choice because it has a very distinct shape. It's about 18 nanometers in diameter, 300 nanometers long, and it looks like a cylinder. So you won't confuse it with any other junk on the end of your on your surface. It has this very characteristic shape. Also, it's very cheap and it doesn't kill you, so it's nice in that way. This is a standard atomic force microscopy image of tobacco mosaic virus on gold. And if you remember what we have to do, the challenge here is we have to put our sample on the end of the cantilever. So we have to find some way to put these viruses on the end of this tiny, tiny silicon lever. And what we did is what you might expect would be the first and stupidest thing to do, is just dip the cantilever in some solution of tobacco mosaic virus. It wasn't quite that simple, but essentially that's what we did. You can see this is the end of the cantilever. There was a focused ion beam that we used to cut this cantilever, make it flat on the end. Some gold was evaporated on the end to make it sticky for the viruses. And then the tip of this lever was inserted in a solution of the virus and pulled out. And then you can see we have a few virus particles attached to the end. Now, of course, this is a scanning electron micrograph of the end of the cantilever. When you take an SEM of a biological thing like a virus, you've destroyed the sample. You burn the whole thing away. So in fact, we took this image after the fact, after we did our MRI. Had we done this before, our MRI wouldn't have shown very much. So here's a blow-up of the end of the cantilever with some virus particles on it. So once we've prepared the cantilever, what we did is scan the cantilever over the magnetic tip. At each point, measure the resonant force and make a three-dimensional map of that resonant force. And that's what you see here. These are X and Y plots of the resonant force at different Z positions. And you can see we get some kind of some pattern. You can see there it has some kind of linear shape here, something that looks maybe like a little bit like a virus. You can see it has this characteristic of having a double image. But from such force images, you can't say very much what we're looking at. So what you should do is think a little bit about what experiment are we doing. Okay, we take our cantilever and we move it in space over this magnetic tip. And there are some viruses on the end of this cantilever. Every time a virus particle, a point virus particle, let's say, goes through this resonant area, this resonant slice, it will produce a resonant force. So if I'm scanning my cantilever with the virus through here, when I go through here, I'll get some signal. Then when I'm in the middle, I get nothing. When I go through here, again, I'll get a signal. Okay, that might start to tell you a little bit why you get these double images. What you should also remember is that the force goes as the gradient of the magnetic field. Now, this gradient is not uniform in space, so it's stronger, let's say, on these sides here than it is up here at the top. So the same point particle of virus, when it goes through here, will produce a larger signal than when it goes through here. So all of this information is very easy to calculate. If you know the shape of your magnetic tip, you can just make a very simple magnetostatic model of the gradients and of the shape of this resonant slice. And from that model, you can essentially make point spread functions, what are called point spread functions in imaging. So if I take a point of my object, of my virus, and I trace it through here, which kind of force map will I get out? So this is the force map I get out if I drag a point at this height through the resonant slice, and this is the force map I will get if I drag the point particle through this height in the resonant slice. Okay, so now we have these different point spread functions for different heights. With this information, we can essentially deconvolve these force maps to come up with the original object which had to have created them. Okay, and we can use a very simple iterative algorithm to essentially take these point spread functions, these force maps, and come up with the object that created them. And once we run that, we get an image that looks something like this. Okay, so this starts to look more like perhaps a virus particle. And if we compare that to the SEM that we took afterwards, you can see that the correspondence is really very good, even up to very small details. Okay, so at this point you might stop me and say, well, you went to all this trouble to make an MRI of the virus, and it looks more or less the same as what you get with an SEM. And that's in some sense true, but if you think about the contrast that's in these two images, it's completely different. So the contrast here is coming from backscattered electrons. Here we're actually looking at proton density in the virus. Also, when I take this image, I've completely destroyed the virus, whereas here, yes, I've frozen the virus. I've taken it down to 300 millikelvin, but I haven't actually burned it away. And the other thing is that this is actually part of a three-dimensional image, while this is just a 2D image. So what I can do is show you all the different slices in 3D, which should give you something equivalent to that slice of Christian's brain that I showed in the beginning. You can see that we can look above the virus, we can look inside the virus, and we can look below the virus. And in fact, I can show a plot like this in X and Y, but I can just as easily take a cross-section here in X and Z, and you will see that there are these little tobacco mosaic virus particles sitting on top of what looks like a uniform film of protons here. So when we first saw this, we were confused as to what would this uniform film be. But if you're a surface scientist, then you know that any gold layer that has at one point or another been exposed to ambient conditions will contain some film of hydrocarbons or water or something like that. And that's actually what we see. We see a couple of monolayers of proton-containing junk on top of our cantilever. And you can do this in various parts of the sample, and even force maps that look messy and crazy like this, when you deconvolve them, actually look like something that is really there in the SEM. So this is just to emphasize the two regions of the sample that were measured. And there was some later work that was done actually to measure the contamination layer, this proton layer that is actually found around a nanotube. So this is a very similar experiment where instead of putting virus on the end of a cantilever, you stick a nanotube on the end of the lever. And then since that nanotube has been exposed to air, it will also have some protons around it. And so you can measure the proton signal around this nanotube, and you will find that it conforms to the morphology of that nanotube very well. So we've basically taken an MRI of the junk around a nanotube. So the results here basically come down to that we have a mechanically detected MRI with sub-10 nanometer spatial resolution. We were able to image individual tobacco mosaic particles, and you have something like a noise floor which is equivalent to the noise of about 35 net nuclear spins. Okay, so now you might ask, how can we do better than that? How can we get to what you originally advertised, which was an atomic scale microscope? Well, the signal-to-noise ratio is actually quite a simple expression. We're measuring variances, so what you have to consider is a power signal-to-noise ratio. And the signal essentially goes as what I've been saying all along. It's the magnetic moment of the spin times the gradient of the magnetic particle. Now, the magnetic moment of the spin you can't change. If you choose a nucleus, you're stuck with a certain magnetic moment. But the gradient could be improved if we could have better magnets. On the noise side of the equation, you have some bandwidth here, which is basically set by your relaxation rates or your experiment. Usually you can't change this very much. But you have this thermal force noise, which is limiting you. And there are various things that go into here. There's the quality factor of your cantilever, the spring constant of the cantilever, and also some other kinds of interactions that I'll talk about just now. So for better magnetic tips, as I was saying, this is some work that's ongoing. There are some more favorable geometries which might give higher gradients, but essentially it comes down to a micromagnetics problem of really figuring out why these magnetic tips that are made are not showing their full magnetization. But if you can increase the gradients that these produce, this will give a lot more signal to noise and make the resolution much better. Of course, part of the way that you could get a higher gradient is, of course, just getting closer to the magnetic tips. So you might ask me, why don't you just go as close as possible to these kinds of tips? Well, there is a limitation, and the limitation comes from something called non-contact friction. So when you have a cantilever hanging like this, and you bring it close to a surface, you eventually start to see a drop in the mechanical Q, or an increase in the mechanical dissipation because of interactions with things that are on the surface. And these kinds of interactions are being studied and just now being sort of understood, but they are essentially the limiting factor to how close you can get to these magnetic tips and how high these gradients can be. And there's some indication that by using the right kinds of coatings on the cantilever and on the surface, you may be able to reduce these kinds of frictions quite a lot. Another way to go about improving this would be to start getting some systems, some much better force sensors. Some sensors like the ones I sort of hinted at might be the future of force sensing, like these nanotubes, or perhaps something like a nanowire like this. The main problem there, if you want to integrate these in a kind of a magnetic resonance experiment, is that you have to try to measure the displacement of these devices. And it's going to be very hard to measure the displacement of these devices using optical methods, for the simple reason that they're much smaller than the wavelength of the light. So you might have to use some kind of capacitive detection techniques or other kinds of detection techniques. Okay, there's been some work to sort of improve on the signal-to-noise with other methods, which maybe I won't discuss now because it looks like I'm running out of time. So with the time that's remaining, I just want to introduce sort of my lab and what we would like to do. Of course, pushing the resolution of such a technique would be nice, but what we would like to do in our lab is to use the current resolution to investigate sort of interesting problems. So what we're building in my lab in Basel is a system capable of coupling these nanomechanical oscillators to mesoscopic transport devices. And one of the main goals there is that we'd like to use existing MRFM sensitivity, sort of resolution on the order of 10 nanometers or sort of something like 100 net spins, to investigate small nuclear spin ensembles, and in particular, small nuclear spin ensembles inside quantum dots, nanotubes, or other mesoscopic systems. Probably many of you here know that nuclear spins in these mesoscopic systems play a very important role. In particular, in quantum dots, sort of small numbers of nuclear spins are responsible for a lot of the decoherence of electron spins inside quantum dots. And as of now, there are no real ways of measuring directly the nuclear spins because there's just not that many of them inside quantum dots. And what we would like to do is to use MRFM to see if we can find out something about these nuclear spin ensembles, and maybe even to manipulate them. These are some early pictures from our lab where we've been able to sort of combine these very sensitive force detection techniques with the sort of electrical samples that are required in quantum dot and nanotube experiments. So what you see here is a cantilever that's being approached to a nanotube SET down here. And we've been working very hard to build a system where we can integrate these two in a refrigerator. And we've also been working very hard at making mesoscopic samples that we can couple easily to our cantilevers. And there are some geometric challenges for that. So here are some nanotube SETs that we have been working on with the students, preparing them to couple to some cantilevers. So we hope to come up with some measurements soon, but the main work so far has been from when I arrived in Basel with an empty lab, getting from here to sort of where we can measure thermal noise of soft cantilevers at 400 millikelvin. That's been sort of the work that's going on. Hopefully the next work will be to tell you something about magnetic resonance in mesoscopic structures. And if you're interested in following us, we have a web page, and I should also thank my collaborators at IBM who are doing a lot of the work that I showed here. In particular, Christian Dagan, who is actually an ETH alumnus from the Bad Meyer group. And also I'd like to just show the students in my own group who will be doing some of the work that we hope to do in the future. So thanks for your attention.
Okay, thanks Martino for this nice talk. Are there questions, comments? Yes, please.
Yes, so that's an excellent. Okay, so the question was, how can we put the magnetic tip on the cantilever, and it looks like it might be more versatile if we could do that. So I didn't show that geometry here, but there have been many experiments with the magnetic tip on the cantilever. And of course, it is more versatile because you can bring it to some, let's say, planar sample. At the moment, the limitation there is that we can't use these nice lithographic techniques like the one that I showed, where we were making these iron cobalt tips through stencil masks. It's very hard to integrate that on the end of a MEMS oscillator. There's been a group in Cornell who's been trying to do this for some time. I think his professor is John Marone, and they had just a lot of processing problems, and they were either getting bad oscillators with good magnets or bad magnets with good oscillators. It was hard to put the two together. But if you can do that, that would really be wonderful. There is one drawback to that, and that is that if you put the magnet on the cantilever, and let's say the cantilever is in some applied field, as that magnet moves through the field, there are going to be dissipation. There's going to be dissipation introduced by the interaction of the magnet with the field, and that will also limit the sensitivity of the lever. So in some sense, it's best to put the smallest, lightest, least magnetic thing on the cantilever in order to maintain sort of the perfect to have the least dissipation introduced into the mechanical system, and to put your strong magnet somewhere else. That's sort of the philosophy that we followed. That's why we put the viruses on the lever. Of course, it makes the sample preparation not so nice. So I think you have to weigh it with the type of sample you're working in, what kind of resolution you want.
Can I ask a question about the MRI? beginning you said the goal is single spin detection,
Mm-hmm.
and now you sort of escape and say, let's go to mesoscopic samples.
Yeah, so I'm taking the easy way out. I think the IBM guys are not going to take the easy way out. I think they will continue to push this.
Do you think there's a realistic chance to get this single spin resolution?
I mean,
Spatial resolution?
it gets harder and harder, of course, but this fundamentally holds. And if you believe calculations of the magnetic moment, we're about a factor of 10 away from what we should have for existing tips in the gradient. That will give you a factor of 100 in the signal-to-noise ratio. If we had a factor of 100 there, it would certainly seem possible, since we now have a noise equivalent to roughly 30 or 40 spins. Of course, there are other problems aside from simple signal-to-noise. I showed this layer of kind of contamination that we had underneath our sample. If you're going to start looking at single nuclei, single molecules, you have to do something about this contamination layer. How can you tell your contamination layer from your sample? So really, if we do ever achieve these very good signal-to-noise ratios, there will have to be a whole revolution in sample preparation. More like STM, I would say. Mm-hmm.
You chose this integration time of
Yeah.
1 minute. So
Yeah. Okay. So it's always hard to quantify this.
why 1 minute, and why could you be better when you just integrate longer?
Yeah. I mean, right. I mean, if you always integrate longer, you can get the higher signal to noise, but it goes as the square root of time. So at some point, you don't.
I was wondering why you're quoting a minute, usually you would quote a second.
Yeah, right. Well, if we quote a second, it's not as good. That's certainly the point. The reason we took 1 minute is because those points in the 3D image that I made were averaged each for 1 minute. Okay, so that you can imagine that was a painful image to take. It's a three-dimensional image.
Stable enough to average 1 hour at each point?
Yeah, well, so the entire image that we took, it was averaging at 1 minute for each point. It took 8 days to take the entire image, right? And that's basically the whole time of that fridge. And so that's basically the stretch of how long we could take that measurement. Of course, you could average longer on each one, but then you would have to have a system so stable that it would survive after a transfer or something like that. So I would say this is sort of the reason we picked 1 minute was because we could make one image with that averaging time. This 35 net spins, there's sort of another part in here. That's the net spin polarization. That's the number of spin up minus spin down, shall we say. There's 35 more spin ups than spin downs. But the number of the ensemble of spins is the square of that, actually, right? So there are many, the number of spins we're looking at is not 35. The total number is larger. How big is this? Well, the resolution that we get, depending on the position of the slice, is somewhere between 5 and 10 nanometers. How big is that? I think that works out roughly too. If you take 5 nanometers and find out how many spins there are, that's roughly the square of that.
Yes. Would it be possible to turn the principle around and measure the relaxation of an individual spin under relaxation?
So what do you mean? Maybe I don't understand. Right.
On a single spin.
Using the mechanical.
Would it be possible if everything else was known to NMR on a single?
You mean what would happen if you were able to do that? Yeah, well, they did basically ESR in a single electron spin, and I think they saw some effects which were sort of like Stern-Gerlach effects at that point. And maybe you would see something similar with the single nuclear spin. But as long as you're measuring essentially, I guess, the spin noise, then, and I basically can't tell you very much about the orientation, so I don't think you would learn very much quantum mechanical about it.
So is there a competing technique? I mean, if you forget about cantilevers and forces and stuff like that?
I think it's one that's been emerging is this diamond, this nitrogen vacancy centers in diamonds. Essentially, there have been a few people, including Christian, my former collaborator, who has proposed them as very, very sensitive sensors of magnetic field. And if you have a very sensitive sensor of magnetic field, then you also have a very sensitive sensor of magnetic spin. These are really nice because they work at room temperature. They're very bright. You can even now get these nano diamond particles with one nitrogen vacancy in them. I think the question there is, can you get these nitrogen vacancy centers close enough to what you're measuring so that the resolution is good? And that's a question of what's on the surface, and can these nitrogen vacancy centers survive when they're very close to a surface? But I think that's the only one that I've heard of that seems plausible for getting as good resolution as this. Maybe that might even be a better way to go, but I'm not an expert in that. Yeah.
And there was the inverse correlation time of about 2.5 kilohertz. This would just roughly correspond to the NMR frequency of fluoride in the Earth magnetic field. Is this just coincidence?
Sorry, so you're talking about this? Yeah, so this is the resonant frequency of the cantilever. So it's the mechanical resonance of the lever. It shouldn't coincide. There shouldn't be anything happening like that. I should really show something that shows a much broader spectrum. But essentially, this is the fundamental mode. This broad thermal noise is actually very sharp. You can see the scale is very zoomed in. That's the thermal noise peak of the fundamental mode of the cantilever. And then on top of that, we put our spin signal.
Okay, I see no more questions, so let's thank Martino for his talk again.